Hi. We are having a lot of contact. First time.
Good afternoon, everyone. Now we have an invited talk entitled Convex Optimization, Tools and Applications in Statistics and Data Science by Professor Balsubramanian Narasimhan of Stanford University, and request Professor Vishwadeva Pradhan of Indian Statistical Institute to please come on stage and chair the session for us.
Good afternoon. This is invited session, invited talk. That is on convex optimization, tools and application in statistics and data science by Balsubramanian Narasimhan. Dr. Balsubramanian Narasimhan is a senior research scientist in the Department of Biomedical Data Science and in Department of Statistics at Stanford University. He is also the director of the Data Coordinating Center in the School of Medicine at Stanford. He obtained his BSc in Mathematics at Noida College, Chennai, MSc in Applied Mathematics at PSC College of Technology, Coimbatore, and his PhD in Statistics at Florida State University, USA. He is an elected member of the Art Foundation. His research interests are in optimization, machine learning, statistical computing, and biostatistics. For 40 minutes and 5 minutes.
Thank you, Professor Pradhan, for the introduction. I want to thank the organizers of this conference, especially Professor Pradita Maji, Day4 Munda, Dr. Paul, and Marsha, who's been very kind and done a lot to make this a very, very nice conference. So today I'm going to talk about convex optimization. And this is, of course, a subfield of optimization in general. However, it's very useful because of the fact that the number of practical applications can exploit it. And so in my talk today, I hope to show you where all you see such problems, and some of them may surprise you, maybe not. And at the same time, it's not just enough to actually show these applications, but now we have very, very good tools to be able to solve these problems. And that's also something that I'm going to highlight. With the result that this talk is going to be slightly different from most of the talks. Not only will you see some mathematical formulations and applications, you'll also see code. And I hope that you'll take that code and actually try it yourself. You should be able to run these things on your laptop, okay? You don't need to go to a big server or do anything. You should be able to run these things. Okay, so let's begin. What am I going to tell you? Optimization is really fundamental to modern computation. And even deep neural networks, all those things are doing either stochastic versions of it or sometimes even direct versions of it. And of course, this is subfield. So we now have the technology to construct and express these problems in software. And the way you express this in software almost follows the mathematical formulation directly. I'll show you examples of that, which makes it very convenient. You have all the tools at your disposal to think mathematically and pretty much translate it directly into software. And there's open source software that's implemented. You don't have to do anything. You can download it on your laptop, run these things. When I was growing up as a graduate student, when you had to solve optimization problems, you had to sit at the god of Fortran, sit down and write all our code. You don't need to do that anymore. It's all very, very easy, so you can think at a very high level. And you can also make use of advanced commercial solvers that actually plug into these things. And there are many applications, as I'll illustrate later. Okay, so let's start with a simple formulation of what this is all about, just to make things clear. We have a function f0 that we want to minimize. Maximization is the same as minimization, it doesn't make it of it. So you have constraints, fi of x, and we also have some equality constraints. So inequality and equality constraints, and we have the vector x, the goal is to find the x that satisfies these conditions. And of course, the kinds of f that you can do this for is not, you can't do it for any x, but the class of functions for which these problems actually have some mathematical guarantees. And for example, if you take linear programming, the f's, the g's, all of these are linear. Okay, so we know, from the celebrated results of, say, George Danzig and so on, that there's a unique solution where it's always to be found at the edge of the polytope. So you can rewrite this problem as in matrix form as minimize C transpose X, subject to Ax less than or equal to B, and X greater than or equal to 0. That's a standard form you can do. You can pretty much subsume them all in this formulation here. Okay, so that's one of the easiest things to understand because everything is linear. Let's actually start with a simple problem here. So this is a health example. I took this from linear programming for dummies because I think I like to start out very, very small. So the goal here is we have we have a minimum total requirement for all these minerals, vitamins, calciums, and so on, that the US RDA recommends. And there are two tablets that supply these things. For example, Vega Vita supplies 20 milligrams of vitamin C, whereas Happy Health gives 30 milligrams per tablet. And similarly for, say, magnesium, the requirement is 360 milligrams per day, and Vega Vita will give 60, whereas Happy Health gives 90 milligrams. And the cost of the two tablets are different. So the question is, what is the mix, for example, that you would like, how can you minimize the costs per day while satisfying these conditions? And you formulate this as a linear programming problem. You'll say, okay, minimize 0.2 x1 plus 0.3 x2, where x1 and x2 are the number of tablets for beta and happy health, subject to the conditions that you need to satisfy, you need to at least make up the minimum requirements. Right? So this is just a bunch of inequality constraints. Okay, so that's the mathematical formulation. And that's linear programming. So what is convex programming? In convex programming, we now let the f's be convex. So again, the objective and inequality constraints are all convex, and the equality constraints are, of course, linear. We assume that. And again, there are many applications of this. So linear programming was the simplest one, but this is a slight generalization of it. And again, just to remind you of what a convex set is. If you have a region in a plane, for example, the set is convex if all the line joining x and y is completely contained inside the set. And so that's and this you can express as, for example, theta x1 plus 1 minus theta x2 belongs to the set for any x1, x2 in the set, and theta will be 0, 1. Okay. And again, if you want to do this in, say, larger dimensions, again, the formulation is again the same thing. F of theta x plus 1 minus theta y is less than or equal to theta f of x plus 1 minus theta f of y. So this is the definition of a convex function. The characteristics of a convex problem, of course, are, which is what makes it very attractive, is that the feasible set, which is the set of all possible solutions to this problem, is itself as convex. And this is the important aspect that we like. In convex programming, the local optimum is the global optimum. Right? So, which means that we know we have a unique solution if it exists. So I want to say that this is a nice quote from the book. Stephen Boyd is a colleague of ours in the electrical engineering department. He's got a famous book. It's online, you can download. And he says the challenge and art of using convex optimization is in recognizing and formulating the problem. So this is the hard part. Once this formulation is done, solving the problem like least squares or linear programming is almost technology. And that's what I'm going to show you today. That the hard part is doing this part here, the first sentence. So in your research, for example, I hope that I can convince you that this is the case. Here are some examples of convex problems in statistics and machine learning. We already know that ordinary least squares, non-negative least squares, logistic regression, all these things are all convex programs. So for example, in least squares regression, we are minimizing the sum of squares. So it's a convex objective. In non-negative least squares, it's the same thing, except we have a constraint that says that you have to be greater than or equal to 0. The coefficients have to be greater than or equal to 0. And the logistic, well, you can actually transform that in one of these. Bridge regression, lasso, and elastic net regression. These are also convex problems. Isotonic regression, where you have a constraint that says that you want to fit a function that is monotonic. That's also convex. Uber, robust regression for minimizing the effect of outliers is one. And of course, support vector machines can also be formulated this way. Sparse inverse covariance estimation. So you want to estimate the inverse of the covariance matrix, except that you know that it's got to be sparse. You can actually formulate this in convex of maximum entropy and many new methods. Okay, so the field is pretty, even though it's a small field of optimization, it's just that the applications are so numerous. That's why it actually has its own book, has its own software, and people are, can use it for solving many things. And even if you don't have a convex problem, for example, you can actually have relaxations where you can actually make it into somewhat like a, you can use the techniques of convex programming to get somewhere. Okay, how do you solve a convex problem? Typically, you use an existing custom solver. So there are companies, there is software where it'll say, oh, give me, you construct the A matrix, you construct the, the FIs, you construct the inequality constraints, and you have to sort of formulate them in a way to a particular piece of software so that it can actually solve this problem for you. Or you can also define your own solver using the, say, maybe some kind of an interior point method or something like that. But that requires a lot of work. And again, we hope that can clear the large problems. Or the other thing you could do is to transform your code problem into a code program and use a standard code programming solver. And this is where we're going. And the point is that this transforming part here is the time-consuming part. This relates to the code that I showed you before. Just doing this transformation is very, for a generic problem, is not trivial. But there are domain-specific languages that can help you in this regard. And again, I'll just briefly mention what these are. So these are just little specialized languages that you implement in your existing software, right? So for example, there are several of these things available for convex optimization today. So there is originally the first implementation of what we're going to talk about, which is called disciplined convex programming, and I'll explain that in a minute, was implemented in CVX, and this was actually written inside MATLAB. So which means you have to have MATLAB, and MATLAB is a commercial product, etc., etc. So a few people use it. But then we have CVX-Pi, which is widely used. It's available in Python. It's free. You can download. If you're a fan of the Julia language, there's an implementation in a thing called convex.jl. That's also available. But today I'm going to talk about CVXR, which is an implementation in R. The reason why I'm doing this in R is because I'm a statistician and we use R a lot. And so it's natural to have these tools available in R so I can seamlessly work with the existing tools in R. So what I want to point out is that CVXR and CVX5, these two are the ones that are undergoing active development these days. And this is developed by Stephen Diamond and his group, who I know very well. And this is developed by myself and my former student, Anshi Fu. We are still adding new features to it as we go on. Okay. So, all right. So that seems like, oh, this is fantastic. We can do this. Of course, there's a small price to pay here, in the sense that if you want to solve a problem very, very efficiently, in the most, without making use of the computing resources in a very parsimonious manner so that you can solve large problems, then you probably have to do some additional work. However, at the time when you're actually doing research, at least I tend to think in large level constructs. So these tools, while they're slower, they are extremely flexible and they allow for fast prototyping. I'll give you an example of this right at the end, that I actually had to do it last year. Okay, so this is a quote I like a lot because this was actually a letter from Karl Gauss to Schumacher in 1843. And he says, all new systems of notation are such that one can accomplish nothing by means of them, which would not also be accomplished without them. But the advantage is that when such a system of notation corresponds to the innermost essence of frequently occurring needs, one can solve problems belonging to in that category, indeed, can mechanically solve them in cases so complicated that without such an aid, even a genius becomes powerless. I think that's really a powerful statement. So he says that thus it is with the invention of calculating by letters in general, thus it was with differential calculus. So I'm hoping to convince you that, you should be thinking of solving convex problems at a very abstract level using tools such as this. So here's a little joke. When I showed this to Stephen Boyd, he says, I'm disappointed that Carl Gauss did not mention our discipline programming paradigm before in his letter. Anyway, so it's just a big joke. All right, so what is the technology? So as I said, you can do this both in Python and R and so on. The reason why I'm doing this in R is because I happen to be a statistician and I use R a lot. For those of you who are not that familiar with some R language, it's just a brief note about it. So it was developed by John Chambers, Rick Becker, and Alan Wilkes at Bell Labs. And Trevor, by the way, was one of the contributors to the first regression and generalized additive models there in S. And then that was a commercial product that AT&T was selling. But then Ross Ihata and Robert Gentleman at the University of Auckland, they sort of started developing an open source version of it. And that's what's become R these days. And the main thing is that it's highly extensible. There's a packaging system, and there are lots of packages for statistics and ML. And by the way, this packaging system had an influence on the Python packaging system as well. So it came a little before Python. And so if you go to CAN, for example, you can see, all right, the time I took the snapshot, there were something like 20,000 packages on CAN. So there's lots of packages for everything from Bayesian analysis to, survey sampling to all manner of stuff. And this task views that you have here tells you what packages relate to each of those topics, including optimization and so on. Okay, so how would we sort of going back to that simple problem that we had before, how would we translate this into, say, R or something like that? So here's a word-to-word translation of this. So I want to minimize, this is the mathematical formulation that I showed you before. And I just want you to pay attention to the syntax here. So you just have to do some little thing where you define, you load your package, and then the unknowns are x1 and x2, and those have to be integers. So you just have to say x is an integer of 2. The cost is this here, so that's exactly written down verbatim. And the objective is to minimize this function. So you want to minimize cost. And the constraints are these. So again, you can see it's just a direct listing of all of these. It's a list. You construct a problem. Okay, here's my problem. It takes an objective, and it takes a list of constraints. You say, I want a solution. So you say, solve the problem. And it goes ahead and solves the problem, and you can obtain the value. You can obtain the objective value. You can also obtain the value of x that gives you the minimum. And if you do that, here's the answer you get. Okay? So this is how it works. That's simple. You don't have to write a linear program or doing anything. It just does it all for you. Okay. How is this all happening? What's making this possible? This is all enabled by this mode of programming called disciplined convex programming. So what is disciplined convex programming? Well, it's a way of writing constructive programs, constructive convex programs. So I'll begin a little bit with some introduction. So we know what a convex function is, a function that looks like this, purely a concave function. And you can also know what an affine function is, which is one that can be, you can write it down this way, or it can be expressed by matrix notation as well. And so here it is. If this affine means it has this following form. So we make use of building blocks like this. And the way you verify a function is concave or convex is by basic definition, which is, you look at the first order, second order conditions and see if it is greater than 0. This sometimes can be hard, especially if your function is complex. The other approach, and this is the difference here, what we're going to do is we're going to construct convex functions using building blocks, like Legos. So if we have a library of basic functions that are concave or convex, what we can do is we can build them up and we can define calculus rules and transformations that preserve convexity. With that in place, we can actually, verify that a function is convex because it's convex by construction. This is an even smaller subset of convex functions, of course, right? But it's a rich set, as I'll show you. So this was the thesis of Michael Grant in 2006, and it basically defined the framework for describing convex problems, optimization problems based on constructive convex analysis. So this is sufficient, but not necessary, right? I mean, these problems are convex by construction, but not all convex problems can be utilized. And this is the basic thing that drives all these tools that I mentioned before, including CVXR. Because by construction things are convex, I can verify things and so on. So CVXR is the implementation norm, and it's again, it connects to many solvers. There are many solvers that are available. Some of them are free, and they are not always the best, although there are some very good ones that are coming on these days. But there are also commercial solvers that are available by very well-to-do companies that produce high-quality software. And if you're an academic user, you can get them for free. And it mixes easily with R code. So if you're an R programmer, you'll see that the syntax is very natural. You don't have to think outside the box. And similarly, if you're a Python programmer in CVXR, you can just do it without much effort. And it uses GCP, which is the discipline convex programming that I mentioned. It's written in R and calls for C++ code for canonicalization and speed. So there are core parts of it that have to be written in C++ for speed. And it's described in our paper 2024. Okay, so now that we have this, I should tell you, here are the people involved in this. So this is Angie Fu, who is my student in EE, together with Stephen Boyd. And she's now a professor at Memorial Sloan Kettering, working on radiology optimization in cancer treatment. So she uses a lot of optimization tools there. Stephen Diamond, he's a driving force behind CVXPy as well. He was Stephen Boyd's student, but now he works for a company that does online power management using optimization. David Kang was a master's student who's now an engineer at Apple. And then Stephen Boyd, of course, everybody knows. He's the author of the famous books and so on, so the author of this programming, etc. So with that, I'm going to lead you through a bunch of examples so you actually see these things in action. Let's start with the simplest one. So linear regression, the goal is to find data that minimize the residual sum of squares, right? And here, Y is a given response, and X is also a given matrix. So Y and X are given to us. The goal is to find data that minimizes this. So how would one go about doing that? So I'm going to lead you through these few steps. So this is the code that will do the regression. And the way it runs it as follows. Okay, you invoke the library, so use the CVXR package. You define the beta, the three-dimensional variable that you want to estimate. You define the objective. It's the sum of squares, y minus, by the way, this is the matrix multiplication in R. So you say y minus x beta. And here's where for those of you who are R programmers, I just want to point out one thing here. Y is a vector, just a bunch of numbers, right? X is also a matrix, it's a bunch of numbers. But beta is not a bunch of numbers. Beta is a special thing that CVXR provides. However, it behaves like a vector. So you don't even see the difference. You just use it without even thinking. and you define your problem. You say, I want to minimize the objective. And you say, solve the problem, and you can print out both the objective value and the solution. That's it. You just have to write this. Okay, so you may say, all right, this is good, but I have programs that will do these things in one line for me. Why is this so bad, so good? You can go even shorter than this. Well, let me change that a little bit. So as I said, I just solve the problem, prints the objective value, prints the solution. So now I'm going to say, oh, no, I just don't want to do least squares alone. I just want to have non-negative least squares, which means I have a constraint. Okay? All I have to do is add this constraint. So I just have to define the constraint. I say list beta greater than 0. So the previous one that we had before, I just have to make sure to add a constraint to this beta here. So I just say, all right, make beta greater than 0, and then it's all the same again. No difference. Okay? All right. Somebody may say, all right, oh, I have another program. I can also have another package because this is one line. What's so important about this? But suppose I now change this and say, hey, I don't want beta to be greater than 0. I just want beta 1, beta 2 to be greater than or equal to sum up to greater than 5, beta 3, beta 4 less than or equal to -1, etc., etc. Now you see that you can't find any tool that will do that for you automatically. But here you just have to add the constraints. And automatically. So here's a plot just to make sure that it actually does the right job. And trust me, it does. And so here's the order solution. Here is the CDXR solution. Here is another solution from another package, and it's all, they all match. So the blue and the green will always match. Okay. So that was one. Yesterday we heard Trevor talk about sparse models. So that's because, you know, you're using regularization to prevent overfitting, introduce sparsity, feature allow for variable selection, etc. So the elastic net, which was invented by Zhu and Hasty in 2005, is one where you actually have a regression with a mix of an L2 and L1 penalty, right? So here, lambda is the regularization parameter. This alpha is a parameter that sort of goes between L2 and L1 norms. So for example, if you have alpha to be equal to 1, then this term goes off. So all you get is this lasso. Right? And if you have alpha equals 0, you just get the ridge regression. Okay. And so this is the pack, this is all implemented nicely in the package BlimNet. So it's actually a specialized package for doing these. And of course, it's going to be very fast. But if you want to sort of formulate this in CDXR, it's exactly the same thing. So we're going to write the penalty part like this. So you have a beta, you have a lambda, you have an alpha. The ridge part is 1 minus alpha over 2 stars sum of beta squared. The lasso part is alpha times the norm 1 of beta. And the penalty is just lambda times lasso plus ridge. So notice how this is exactly expressing this part here. It's exactly that. There's nothing special. So once you have that, you can just say the loss is sum of squares of this, and then objective is loss plus elastic regularization. And once you're given x and y and lambda and alpha, whatever, you can just run this through, and this will solve the problem for you. Nearly isotonic regression. So I'm progressively getting to more and more involved problems, as you'll see. And again, you'll see that it's very easy to express these things using this constructive convex atoms. So you want to minimize a sum of squares, but you also want some kind of a monotonic relationship, right? Not exactly monotonic, but almost monotonic because you've got a penalization parameter here. So what do? You have a function again that for this term, or this part we know how to do that because it's exactly the same as before. So here we have to express this one. So the only thing to remember is that once you have a y and lambda, you define the variable to be beta, and the penalty is the sum Pos gives you the positive part. Diff gives you the consecutive differences. Okay? And so that's it. The objective is 0.5, the sum of squares plus lambda plus penalty, solve, and there you get the value. So to solve this whole thing, just took a few lines of code, and here is the result. So this is an example where these are actually global temperature anomalies relative to the 1961 to 1990 average. Okay, so we know that the Earth is getting warmer and warmer, and so you're going to have some kind of a monotonic fit, right? Nearly monotonic fit, not exactly. So using the operator, this diff operator, this actual formulation here, exactly this formulation, we can estimate this isotonic fit. That's how it looks. I've got all these piecewise linear functions here. Now, the important thing to remember is that what is this band here, right? And this again points to the power of this kind of an expression. These are confidence intervals. And the way I can construct them is by bootstrap. So even when I don't have, say, a formula for a statistic or something like that, I can actually just use bootstrapping to compute these confidence intervals. Everything just goes through. It's simple, just resample, prefit, and so on. So you can just go through that. All right. Suppose you wanted a more smoother fit. You didn't want this piecewise, but wanted a slightly smoother curve. Can you still do that? Yes. All you have to do is to go to second order differences. And that's again easy. The only change I need to make is I say diff difference equals 2. I don't need to change anything else. And then if I fit it, here's a smoother fit. And again, I can bootstrap this and so on to get the confidence intervals. Okay. Sparse inverse covariance estimation. So now we're getting to semi-definite matrices and so on, which is again very important. You have to do as statisticians, right? We do this all the time. So suppose you have samples from a multivariate normal, and you know the covariance has a sparse inverse because it reflects some structure. And one way to estimate this S is by maximizing the log. You can do MLE with a sparsity constraint. And the objective here turns out to be this one. And this objective is actually the log likelihood partially maximized using the MLE for the view. Okay. So this is a term, log determinant of S minus the trace of S times Q, subject to the condition that we want the sum of all the entries to be smaller than a penalty, or smaller than a budget. Okay? And this Q is the sample covariance. So this alpha controls the sparsity. If I make alpha very small, then all the entries are going to be almost zero, right? Okay, and the way you express this problem is in these 4 lines. You say define a semi-definite matrix of size n. Here's the objective, log determinant of matrix trace. Construction, the constraint is the fact that you want the sum of the absolute value of S to be smaller than alpha. And same thing, problem, maximize this objective, subject to constraint, solve, get the value. So the semi-def restricts the variable to the positive semi-definite code. That's why we're talking about code programming here. And this log determinant of S must be used rather than log diff because determinant is not a supported atom. They need not be. So this construction, these kinds of tools are provided for you to actually express these problems. And how does it work? So here's a true inverse here. It has this structure. If I use alpha equals, say, 10, you see that there are a lot more patches here, which means a lot more non-zero entries. As I decrease alpha, I get fewer non-zero entries. And I go to alpha equals 1, I get this one. So probably I would choose something between alpha equals 6 and 1, maybe 4. That's pretty much closer to this one. Okay, so I told you here that this you have to use log determinant S instead of log of determinant S because there's no way to infer the convexity of this. So how do you know which ones to use? So we have a huge table of all the things that you get. Think of these as your Lego building blocks. Okay? So these are all the kinds of Tetris blocks or whatever you can use to build your function, compose your function. So notice that you've got things like the harmonic mean, the largest eigenvalue, the sum of the k largest eigenvalues. All of these we can actually derive the convexity properties of. Okay? Small log determinant, log sum x. Those of you who do logistic regression, this thing is what you need. Similarly, all the standard things, entropy, Kullback, Leibniz, divergence, scale divergence, Hoover function. Diff was the one we saw, for example. And then H stack and B stack for actually slapping things together. So all of these are available. So you can go, and I'll give you later resources where you can look at all the things, and we are adding more. We keep developing and we're adding more of these. Okay, when I took optimization course in college, I remember I was really fascinated by this. This first problem I was taught was this one. It's called the catenary problem, right? What is the shape of a freely hanging chain fixed at two endpoints? We see this on the streets all the time, something like this, spider web, power lines, all these things. We know that the answer is a catenary. Again, this is the formula for catenary. But in 1690, Jacob Bernoulli posed this as a problem to all the mathematicians we know. So, of course, Euler solved it, I think. And one way to solve this problem is actually to discretize it. What you can do is, you can think of the endpoints as 0, 1, and 1, 1. So, the height is the same. And you have n discrete chain links. The length of each link is, say, some number h. The potential energy is the sum of the y coordinates, right? Because that's how the chain is hanging. And of course, we want to minimize the potential energy. Right? So the optimization problem is minimize the sum of the yi's, subject to the boundary conditions here. These are the boundary conditions that tell you where the chain is fixed, anchored. And this is the length of each of the link, and that has to be less than h squared. And so if you fix, for example, some numbers, let's say you fix the length of the chain to be 101, the number of discretized points to be 101, the length to be 2, and the total length to be 2, and then h is just n over n minus 1, then you can just write out this problem. X is variable n, y, objective is to minimize the sum of y, and the constraints here, these are the boundary conditions. And this, again, you recognize is just a diff going back to this xi minus xi plus 1 because it's a connected chain, right? And you solve this problem, and here's what we get for the picture. The blue line here is a theoretical result, and the red line is the numerical result. And it's pretty close. Okay, so this is a nice curiosity and so on and so forth. But I'll add a little twist that again says how these kinds of problems, again, if you have, even in mechanics or whatever, if you have these kinds of problems, there are cases where you may not be able to get a closed form solution. You need tools like this. So here's a picture. Look at this one here. The x and the chain is not hanging at the same height, number one. And there could be some obstructions here, right? Sometimes you can have obstructions in these kinds of things. So here I'm going to sort of idealize that in terms of a function g. The g function is a step function. I want, and here's one end of the chain, and here's the other end of the chain. Now I want to know what is the shape of the chain that hangs this way. So this is not something you can solve in a closed form. However, if I make it even more complex, you can't solve it in closed form for sure. All I have to do is to say, okay, I'm going to change the constraints. My constraint, again, here, this is the boundary condition, and here is the same condition as before, chain length. And then I just specify the G function. I say, okay, I want Y to be greater than or equal to G. That's it. And here's the solution it produces. And it's interesting what the solution it produces. Yes. So we have, in some cases it actually lies down, in other cases it actually stays above. So, okay, so I have just 5 more minutes, and you can certainly have a look at my slides later if you want. But how does it work? I'll just tell you what's the technology that makes these things work. So convex expressions are constructed using building blocks called atoms, and these atoms are programmed in a way that they have information about the domain, the dimension, the sign, and the curvature. So this information is used when we compose things together. However, sometimes we also need something more. We have to derive gradients and so on. Okay? And we also have to derive what are called canonical representations. And these are the epigraph or hypograph of those functions. And these have to be implemented as a discipline convex feasibility problem. And this is the part that is very, very a little hard. So not everybody who has not taken a course in advanced convex optimization can do this. But once you've done it, you get an idea very soon. And so this is a way of you can even define non-differentiable functions in terms of this stuff, which is what lets us do things like lasso and so on. Okay, so I want to leave you with a few recent applications. So just last year, we had a person in the medical school come up with an idea that nowadays we are gathering information on patients who are, like cancer patients. We have imaging information, we have demographic information, we have genomic information. We think all of these may contribute to the cancer. How can we use all this data together to get a richer data, perhaps a richer model that can explain the prevalence of the disease? Right? This is the problem. So this is a common problem that's there today. So one thing is that there are 2 easy approaches. Let's take the example of just 2 of those kinds of data. Let's say you have imaging data, imaging features, and you have demographic features. You can fit a model to, what you could do is you could just slap them both together in a big wide X matrix and do your prediction. That's one way. The other way is to say, all right, I'm going to fit each of these models separately. I'm going to use X to predict Y. I'm going to use Z to predict Y. And then I'm going to combine that into some kind of a final prediction. If it is logistic regression, I may do some kind of voting or something like that. Who knows? Right? I can combine them. So the first one is called early fusion, and the second one is called late fusion. But we have a new method that we wrote up, and this is Daily Ding, student in our biomedical data science. We actually can go in between these things smoothly by means of a convex formulation. And the convex formulation is the following. You combine the lasso penalty with an agreement penalty. The agreement penalty is here. It basically says that the data used share some underlying relationship that can be used to center the signal. So in other words, you don't want too much of a disparity between the two. You want to minimize this gap. And this is a tuning parameter. And this approach is powerful when you have some underlying latent variable that you think affects both of them. So, and similarly here, each data may have its own idiosyncratic noise, so you may want to also regularize it to reduce the noise. And this was prototyped using CVXR, and then we generalized it as a package in R, which is a little bit different. So there are a whole bunch of applications here. For example, there's people using CVXR for knockoff e-values, for double machine learning, for ranking and selection. These are all papers I just saw. I just sort of scanned an archive and put it in. And for example, here in medicine for dose response, GLMs and GAMs. So I think people are finding it useful to express all these things at a high level without having to get into the weeds. Okay, so finally, I just want to say that CVXR is a powerful tool for experimentation, prototyping, verification, and you can think of it as a high-level abstraction step, especially for your new method, especially when you have an optimization step. I mean, you can't solve it in closed form. Even if you have it in closed form, actually, this is easier, I would say. Okay, so with that, I'll just conclude with this website. You can, I saw that people were actually using QR codes, so I made one QR code this morning, if you want. And I just want to say that we are excited that soon we're going to have version 1.8, which will have far more, a much larger, much richer library of atoms. And with that, I thank you, and some references for you.
It's a nice presentation and useful idea. So now we have time for the questions and comments discussion. Yeah.
Thank you very much. Actually, you have talked about all the detail of providing solutions and all. I understand you keep it of a regression. Suppose that X transpose X is a singular matrix. Now you are to take care of that.
Oh, yeah, of course. Yeah, I think that it
What
will,
are we getting?
yeah, it'll actually tell you, at the point when it solves. So the part that the tool does is it takes your problem and translates it and sends it to a solver, right? That solver will tell you that the matrix is singular.
Thank you very much for the excellent talk. In the starting, you mentioned about the convexity and the condition for that. So I believe that is actually a projection theorem where the variable that we want to optimize needs to belongs to the Hilbert space. Then only these all assumptions will be valid. If it doesn't belong to Hilbert space, then the existence of the minima, that is the error being minimum, and its uniqueness is not guaranteed.
Yeah.
So that part I think you need to mention.
Yeah, so I think that so, but here, for example, in our case, we are constructing things by construction. So everything you can construct in our system will be convex. So I'm only saying that if you use the disciplined convex programming approach, if you can express your problem in that formulation, you're okay, you have no problems. But in general, what you're saying is true. Yeah, that's always true.
Thank you for the mention. The question was partly asked, but still, what would you recommend for non-convex situations? What's the best way, or just avoiding them?
So that's a hot topic now. Non-convex outputs. So there are many methods, and again, there is no one catch-all method or anything. It all depends on the domain. So, for example, there are domains where you know something about the function where it may have convex behavior in certain regions. In other cases, so which means that you could actually, even in high-dimensional cases, you may be able to do something about it. But a lot of the techniques that people use for this are, they use variational inference and things like that, where they're actually finding a projection that is closest in the subspace that it can actually reach. So those are all, again, I think that there are theorems that are proved that guarantee some degree of closeness to the solution in certain regions. But I think that it's not I don't have a nice enough tool like this to actually give you for a non-convex problem. That's always difficult. Non-convex problems are, each one is its own beast in some sense.
Thank you.
Yeah, any other questions? Okay, so just have one small question. This mixed integer programming problem. So is there anything
So so yes, actually the answer is this one. You can express your mixed integer programming in this one too. It will solve it. What it will do is, so the question is, how do you solve mixed integer problems? So these are not, for example, things like you can't have convexity theory and so on. But the point is that what this will do is it will transform the problem into a form that it sends to a solver. And if you use a solver that actually can solve integer programming problems, it'll give you a solution. So if you look into resources, I want to say that I would point you to this website. So if you go to this website, for example, you can actually see an example, worked out example. So it's all, yeah, we've thought about a lot of those things. But in general, again, it's because if the solver is available.
Very much applicable in many areas.
Yes. Yeah. So again, I think the days of you writing the code in hand and so on are gone. You should be using tools like this or CDX5 to do your stuff. Because even your mixed integer programming problem, for example, and some of these solvers can solve huge mixed integer programming problems. I'm talking about things that have, say, 1,000 variables or so, something like that. Some cases, yeah. Or maybe 10,000. And some Gurobi is one of the famous ones. This one. This is actually known for mixed integer programming. And it's free. You can download it for your academic use.
Okay, thank you. Let us thank the speaker.
Thank you, Professor Narasimhan, for this informative talk. And thank you, Professor Prodhan, for conducting the session. Now, request Professor Prodhan to please felicitate Professor Narasimhan with an memento. And request Professor Puditru Mitru of Indian Institute of Technology, Kharagpur, to please come on stage and felicitate Professor Prodhan with a memento.